Good morning. Welcome to Krishna's class. We continue with our exploration of the concept of uniform continuity, which we left somewhat in the middle with some remarks on the function fx equal to 1 by x on the interval 0. So let us once again start from there. So let f from R be a real valued function defined by 1 by x. Now f is continuous at every point on 0. Therefore, it is a continuous function. Therefore, it's a continuous function. Continuous function on 0. So let A be a point 0, 1. Let us look at the definition of the continuity. We say that f is continuous at A if given epsilon positive, there exists a delta positive such that x minus a less than delta zero 1 implies fx minus now one can easily work out what is this delta based on epsilon. Okay. So what is this actually? See, this is going to be okay. So let me just work it out to see that fx equal to 1 by x. So fx minus equal to 1 by x minus 1 by a. This is equal to a and x are positive, therefore this is so. Now you see what we want is mod fx minus fa is less than epsilon. Want to keep this means mod x minus a divided by ax is less than epsilon. Now if, okay, since a is positive, and a by 2 is less than a. Therefore, see, we can do the following. So, you see that mod x minus a by ax is less than so for a by 2, but x less than a. So, or what we write is this: a by 2 less than x less than a by 2 is 1 by x is greater. See, 2 by a is greater than 1 by or 1 by x is less than 2 by a. That is therefore this becomes less than divided by a into so this is equal to 2 twice x minus a divided by a square. Now keep so you have this less than, so you keep mod x minus a as, write this as, what is it? Or you choose keep delta equal to epsilon into a square divided by, you know that a gets closer and closer to, then is so we have worked this out. This is equal to mod x minus a divided by ax, which is less than twice mod x minus a divided by a square. Now choose. So with the choice of a square, you see that mod fx minus fa is less than epsilon for this choice. Okay. So the so you see that the choice of delta so the choice of not only on epsilon but and as a goes to, these are all qualitative observations, a goes to 0, a goes to 0, we have delta going to delta also goes to so one observes that there does not exist a delta independent of epsilon, independent of a where the continuity is investigated. This is the qualitative observation. You see, a goes to 0. So this is the scenario. You have one chosen a, and what I have done is chosen a by 2, so that you are still greater than 0. And now what we have found is that there is some delta that you can choose for any choice of epsilon. You can have a corresponding delta. So in general, the delta depends on, obviously delta depends on epsilon, but here one cannot choose a delta universally valid for all points 0. Now this is the problem. So f is continuous at A, but not uniformly continuous. That is a situation where given an epsilon, you can find a delta that works for all for every choice of for all points on that interval. So this is the problem. On the other hand, see this one, the same problem. Consider fx equal to 1 by x for x belonging to a, say 1, the interval a1 where a is strictly positive and given. Then what happens? See that once again you go through the analysis, you see that fx minus fy. If you estimate, this is going to be by y, and that's equal to mod x minus y divided by xy, where of course x comma y belong to 1. Now you can show that this is less than or equal to a square. Okay. Therefore, if you want to make this less than epsilon, all that you need is choose mod x minus y equal to epsilon times a square. Then and see this is positive. So then delta is positive, and for this delta mod x minus y less than delta implies mod fx minus less than epsilon for every x comma y belonging to the interval as long as a is positive. So this is therefore we can a delta independent of x comma y and depending only on epsilon such that the continuity condition is satisfied. For all choice of every choice of hence it is uniformly continuous. We say that f is uniformly continuous on the interval positive. But what happens is that as A goes towards 0, then you see that the delta goes to 0, because you are going to have this kind of scenario. The estimate of delta would be something like what we have done here. Delta we are estimating as epsilon a square. So as a tends to 0, delta goes to 0. So the closer you are to 0, the delta becomes very small, but nevertheless a delta exists. Now you can see our graph of this function. Something like this. This is the function. Now you see that if you are here, so if this is your A and you are beyond this, then you see that you can find a delta. Suppose this is the point X, this is the point Y. You see that you look at this one. So if you were to fix a neighborhood of X, say epsilon neighborhood of this, then you can always find a delta neighborhood here. But the limits, I mean, you can see what kind of so this is fx and this is fx. This is fx minus epsilon. Sorry, fx plus epsilon, and this is fx minus epsilon. These are the points that you have. Then there is always a choice of a corresponding delta. As long as you stay away from 0. But the behavior of this delta is clear from the graph, that as you move closer and closer to this, no matter how large an epsilon you choose, the delta will be going towards 0. So there is no universal choice of delta for which this function is continuous at for a given, the condition of continuity that given epsilon positive there exists a delta, and this delta will certainly depend on locally, and as you move closer and closer to 0, this delta is going to go to 0. So let us now frame the definition of uniform continuity. So this is an example which throws a lot of insight into the problem. So definition. Let matrix spaces. Let f be a function from be a function. We say that f is uniformly continuous on x if for a given epsilon positive there exists a delta positive such that whenever are such that T of less than delta then dy of fx1 this is the definition. So once an epsilon is given, you can find you have a universal choice of delta such that for all x and y or x1 and x2 belonging to x, you see that the continuity condition is satisfied in this way. Then you say it is uniformly continuous. That's the definition of uniform continuous. And if you carefully observe that our example satisfies the condition whenever a is positive and we are discussing the problem on the interval a to 1. But whenever we discuss the problem on the interval a to 0 to 1, then you see that there is no such universal choice. What happens is this. See, naturally when for a given epsilon, you fix epsilon, delta has to be small. And we have seen that as A moves towards 0, see, this has to be going to 0. That's the problem. So usually to check this uniform continuity, what you do is we link an estimate of fx minus fy, modulus of fx, or the distance from fx to fy, with the distance from x to y. Usually we try to estimate dy of fy in terms of then it is easy to analyze this. Second remark, suppose then we can define continuity, uniform continuity, on A as follows. F is uniformly A if for a given epsilon such that whenever x1, x2 belongs to A, are such that less than 6. So this is true for every x1, x2 belonging to A. That's why we found. So our observation is that third remark, the example is uniformly continuous on A1 for every A positive on 0. Now this is what we have observed. Now I think having got the definition now, we shall just look at some examples. Take F samples 1. Take F from with A strictly positive. So on this, you see that F of which is less than U square. Because you know that x1 and x2 are both greater than A. So given epsilon, choose so that belonging to A infinity. Therefore, uniformly continuous on on A infinity. So we consider here also we can observe that as A tends towards 0, so we remark A tends to 0, we have okay. Now let us take example 2. Second example. This is the one that we were looking at. R with gx defined by 1 by x. Now observe that if x equal to 1 by n and y equal to 1 by 2n, then they belong to the interval 0, 1. N greater than or equal to. Greater than or equal. Then suppose we will first try this out. So we have take nm then what you have, then we have this is equal to, and this is greater than or equal to 1 whenever n is not equal to so we use this to show that G cannot be continuous. What is the reason? Zero one. For if it were then for epsilon equal to 1. Okay. But this is not possible. Why it is not possible? Let us look at this. Given such a delta, we can choose n greater than 1 by delta. This is positive. This is by Archimedean property. Then for x equal to 1 by n and x equal to 1 by 2n, y equal to 1 by 2n, we have mod x minus y is less than delta, but mod this is equal to n. So you see that this is not possible. Thus, I think I was using G, no? Or else I have used it. Okay, this is right. Thus, G is continuous at all points but not uniformly continuous on 0 1. That's the argument. Now let us do a similar example. 3. We take f from R square. Now we observe that as mod x goes to infinity, x square infinity. And you know the graph of the function. The graph of the function is this, as you know. So as x tends to plus infinity or minus infinity, see that it goes to okay. So as x tends to infinity or x tends to plus infinity or minus infinity, this happens. Now we make two observations. One, f is not uniformly continuous. However, two, f is uniformly continuous on every bounded interval so these two things you can have. Now let us give a rigorous proof. Now this is the first one is guesses. So let us do this. So choose minus a. And take equal to to NH. So given epsilon positive, there exists a delta positive such that mod h less than delta is unrealistic. Why it is 0? See, for instance, given epsilon, suppose there exists such a delta. Okay, suppose there exists such a delta. Now you can choose such that fx is greater than we shall investigate this. Now, see, if this were true, this contradicts the Archimedean property. That's the argument. So let us investigate this. So for epsilon equal to 1, assume that there exists such a delta positive such that mod fx minus fy less than 1, for every see what happens is, suppose you fix 1 x and y, okay, fx and fy. This distance as well. Now what happens to x and y? Now move this upward, this interval 1. What happens to this interval? As fx and fy moves with a distance of 1, such that fx and fy goes to plus infinity, then you see that the corresponding x and y moves towards the right, and x goes to infinity, y goes to infinity. But what happens is x and y becomes smaller and smaller. Okay, so that's the argument that we have. So for example, for take x equal to n and y equal to then what happens? Then if one by n, and what happens to the corresponding, say we take this less than that is possible. Equal to 2 plus 1 by n whole square, and this is greater than or equal. Therefore, you see that this is going to be greater than or equal to 2. Okay. So you see that you cannot make, by making n large enough, you cannot make this greater than 2 as long as you take the points x and y as n plus n and n plus 1 by n. But universally it should be true. So here we are showing a case where it doesn't work. Therefore, cannot make it arbitrarily small. Valid in all cases, all choice of x and y by choosing n sufficiently when n becomes sufficiently large. On the other hand, if we take a to be equal to finite and fx x square, then what you can do is this. This is equal to which is less than or equal to twice m. So given epsilon, choose delta to be something less than epsilon by with this choice. Therefore, it is uniformly continuous. So, on all bounded intervals, the function is uniformly continuous. Now, one can suggest some workouts for this. Some of the simple things where you get uniform continuity. Now we shall do more in the form of general theorems with some more properties introduced. Until that, we shall just leave it at this moment and then wait for more properties of the sets to be, topological properties of the sets to be explored. And then you have the natural questions. Can you connect it to the nature of the sets or the function, and how some general theorems can be proved in this regard. So that we shall postpone for the time being, because we need more sophisticated properties to be discussed before that, and after that we once again revisit this continuity. And when a continuous function is the question, when a continuous function from x to y is uniformly continuous. So the question that we want to explore in future is a general question. Now this question will be explored after introducing some more sophisticated properties. Okay, we'll give some little examples where you can put your hand on. Now the fourth example that we look at is this. Part 1. Take f from to r with fx equal to 1 by x to the power n explore with 1 by x square and then generalize it. It's quite easy to do it. The second problem that you can easily explore is this. Suppose T is a linear map from Rn to Rn. Rn. Then T is uniform. Now, what you have is this. See, here, the crucial thing that you have is this. If T is linear, then you have, say, suppose fx equal T is linear, then what you have is this. See, distance Rn is the range space, and there is a result which says that T is a bounded linear operator, which means it is equal to norm of T Rn times now, of course, the norm is defined in the usual way in Rm and Rn. In Rn, the norm is defined as for x equal to and so also for Rn. This is the norm. Now the norm that you have over here is this. Come to Rn. Now this, you can show that this is a norm. And this exists and this is bounded. That is, so one can show that complete. Okay, now these are all results from non-linear spaces. So those who are not familiar with it, just forget it. Otherwise, use this. Therefore, what you have, so the consequence is that D Rn Rm sorry Rn is equal to norm of this is on Rn, which is equal to norm of P of x minus y on Rn. And further, what you have is this. And norm of less than or equal to norm of P sorry Rn. Okay, so that is we have, and this of course is less than or equal to the bound k times d of so that's what we have. So we get the following result: d Rm Rn dx dy xy. So k is some positive number because the linear transformation, all linear transformations from Rn to Rm are bounded linear transformations. So corresponding to each linear transformation, there exists such a k. And the consequence is that is what? So then excellent. less than. So T is uniform. Map from it's a function. Alright. So those who have done linear algebra and also normed linear spaces, this would make a lot of sense. It involves some basic results on what are called the linear transformations from on finite dimensional vector spaces. Now the third problem is this. Suppose f from R to R is such that f derivative exists and is bounded then a simple application of the mean value theorem. Mod and this is of course less than or equal to mod f derivative of x naught y, and you see that since bounded, see here we apply mean value theorem. Bounded we have now it is quite easy to show that. So for a given epsilon positive, delta to be equal to epsilon then you have uniform continuum. Such an f is uniformly continuous. Now Another problem that you can look into is for suppose you have xn is a sequence in x is a metric space. Now define f of x to be equal to infimum of then one can show that this is uniformly complex. Then the function you are talking about is a function from and then show that. So one can there are other problems which we shall discuss later. Now one can show that as an application. So 3, 4. Any uniformly continuous function where x and y are metric spaces. So this is simple. You estimate this. The distance between this you have to estimate. Okay. And you have to link it up with dx and xn. So you show that this is less than these two, you connect. Okay. So we have to work on this. That is given. So we have to, since it is continuous, No, no, this is okay. I'll say F uniformly is such that the distance y whenever dx less than delta. So this is true for the given choice of epsilon, there is a delta. Now you use the Cauchy nature of this. Okay, what about this? So dx sem, sorry, dx fxm is less than epsilon in delta. Okay. So what we do is we start with an epsilon positive. So begin with an epsilon positive, compute the delta, and then use the Cauchy property. So begin with and use continuity to fix positive. Use Cauchy property of xn to fix n, and then So that shows that this is a Cauchy sequence. Now what you can show is that converse is not. Why the converse is not true? What is that you have to show? Suppose a Cauchy sequence is back to a Cauchy sequence, then can you say that it is a uniformly continuous function? Okay. Now this problem I leave with you. Okay. So with these remarks, let me conclude today's talk. So thank you very much. And after this, we plan to introduce the concept of what are called the compact sets. So in my next lecture would be on compact sets. And then often in between, we will be returning back to this uniform continuity. Thank you very much.